So, welcome to today's lecture. Thank you for coming to today's lecture. This is another lecture of the course on Cyber-Physical System Fundamentals. It's the 14th lecture. This is the second lecture that corresponds to chapter 4 of the companion textbook. That is the chapter on system software. Just to remind you of the context, this is the overall structure of the course. The different boxes here are labeled with the chapter number, and you can see that indeed we are right now in this chapter 4. In chapter 4, I'm discussing system software, operating systems for embedded systems, and also middleware. I'd also like to remind you of the motivation for looking at system software. The key motivation is that we have to cope with conflicting requirements. On one hand, we have an increasing design complexity, and on the other hand, we have stringent time-to-market requirements. That means more and more complex systems have to be designed in rather short amounts of time, and the key question is how do we address the conflict between the two? And if you ask people for possible solutions there out of that problem, people will typically mention the reuse of components as a key idea for coping with that inherent problem. So therefore, we have to try to reuse knowledge from previous designs. Such previous knowledge is also called intellectual property or IP. Now, from my point of view, IP includes both software and hardware IP. Many people just constrain the use of that term to hardware IP, but I think software IP is very important as well. Implicitly, we did already look at hardware IP when I discussed hardware in the third chapter of this companion textbook. And in the last lecture, I looked at operating systems for embedded systems. What I'm going to do today is I will look at middleware, and I will look more particular at communication libraries and at databases. So communication libraries were already mentioned in the overview table that I used to structure the different contents there in the second chapter. There you might remember that we discussed the last row, which is the row describing the imperative model of computation, where I said that for these languages we can use libraries in order to provide message passing. For shared memory-based communication, it would be okay just to have some support for critical sections. However, it's of course a little more convenient if we have nice libraries available that simplify our lives there in order to implement communication easily also for shared memory-based communication. So therefore, I added libraries there with respect to the corresponding diagram that I used in chapter 2. So first of all, I will look at libraries that help us to implement shared memory-based communication. I will present two examples in this context. The first example is an example called pthreads, where pthreads stands for POSIX threads, and POSIX is a standard for operating systems. So what pthreads is doing is it's providing a library that corresponds to that standard for operating systems. As I said, it's supporting the shared memory-based communication. Pthreads provides a standard application program interface, and even though it was initially designed for just a single processor, it can now be used for multiple processors there as well. And pthreads, the pthread library includes the logs, includes the mechanisms that are needed to provide mutual exclusion. And I would like to present an example there, an example of the use of pthreads. So in this example, we are initially creating the memory space that is required for these threads. Then we will be initializing these threads. In total, we are going to have n different threads. And then in this for loop, we are creating these threads. So these threads are created here and pointers to the corresponding data structures for these threads are made available in that kind of array. And we're initializing the attributes. Next, you can see how we can actually use the communication library in order to exchange information between one thread that is sending messages and these other threads that are reading these messages. So the thread that is sending these messages is using a call to that pthread library in order to actually send a message. It's protected by mutex so that the read operations don't interfere. And then after the whole message has been copied into that shared memory area, we are unlocking that thread. And then these threads that are reading from that area there in the memory, they have to first lock that corresponding resource so that they don't get inconsistent values there out of the memory. Then they will be receiving the message and then they will unlock that resource so that others can read that memory area there as well. And finally, we are waiting for all these threads to finish before proceeding with the execution of that code. So that's a little piece of software using calls to the pthread library, where we see that the calls to this log primitives are explicit. So when we try to summarize what we learned about pthreads and when we try to summarize in general properties of pthreads, we come to the conclusion that pthreads are providing us with a standard application programming interface. Obviously, logs are available. In addition, we could be using conditional variables, which are also a means of implementing synchronization. You have seen from the example that synchronization is indeed completely explicit. We do have to call the corresponding library methods here. Also, if you look at more complicated examples, you will see that synchronization is very hard to program correctly. We have seen an example there already contributed by Edward Lee. That was one example where the producer-consumer problem was very difficult to program correctly. The pthread model is supported by a mixture of hardware and software. The shared memory is contributed by the mechanisms implemented in hardware. And then on top of that, we have thread management that is implemented in the software. So we use that combination of hardware and software in order to implement the pthread library. Unfortunately, the exact semantics are depending on the so-called memory consistency model. The memory consistency model tells us what we can actually see from the memory, how we make the views on the memory consistent if we have multiple concurrent threads. And there are different ways in which the view on this memory can be offered. And unfortunately, the semantics of pthreads is not independent of what's provided there in hardware. Also, if we try to implement something rather simple like the producer-consumer problem, then we have to assume some not so well-defined parts of the semantics of the underlying hardware, and therefore it could happen that we have an implementation that works on one computer and doesn't work on some other computer, which of course is not very nice. So therefore, pthreads is a library that is available for parallel programming, for shared memory-based communication, but all the programmers are hoping not having to have to program using that library because there are so many problems. Pthreads are a good backend for other ways of implementing communication, but it's not a level at which programmers would like to program. Pthreads are used as a backend for one approach that is a little more convenient, for one approach where communication is a little easier to program. This is an approach called OpenMP. OpenMP is also targeting shared memory-based hardware, but there we are expressing the parallelism in a different way. There we are using pragmas, and that means, for example, if we would like a certain loop to be executed in parallel, we can precede that loop by a particular pragma. This is a pragma, and then we use this term OMP for OpenMP, and then we specify how we would like that for loop to be executed, and then the compiler tries to automatically parallelize that loop. In addition to that, we can also try to execute other segments of code in parallel, like, for example, certain sections can be executed in parallel, and then there are certain so-called reductions, which means that we are starting with some array of a higher dimension and then reducing the elements to a lower dimension. Like, for example, we could compute the sum of all the elements in an array. That would be a special case of a reduction computation. As you can see from this example up here, we are expressing what we would like to execute in parallel, but we don't have to explicitly express where we would like to compute something. We are not expressing explicitly how we would like to distribute the computation among different processes. Also, the communication is not indicated by the programmer. We don't have to indicate synchronization in contrast to pthreads, where we had to indicate synchronization. We don't have to do this for OpenMP. And also, data distribution is automatic. We had to do this manually for pthreads, but we don't have to do this for OpenMP. However, the advantage can also turn into a disadvantage. If we do have some knowledge about the underlying hardware, then we would possibly like to manually distribute the data over the different processors, and this is not possible with OpenMP because it's relying on these simple pragmas, and they are not sufficient to really explicitly distribute data. So these were the two cases of libraries that are targeting shared memory-based communication. Next, I would like to look at libraries that support message passing. And the first library that I would like to mention is the standard for libraries that are linked to a standard for operating systems. This is the so-called OSEC VDX standard, which is not an operating system by itself, but it is just a standard for writing operating systems. And linked to that standard, there is a standard addressing the need to communicate between different nodes there in a car. These different nodes in a car are typically called EXUs, or execution control units. So this communication can be achieved by this standard for communication in the automotive domain. The standard provides a so-called interaction layer that can be used if an application programmer would like to exchange information there between the different EXUs in a car. This layer is designed on top of two lower layers that are actually performing the communication. There are the network layer and the data link layer, and these two layers are closer to the actual means of communication that we're using there in the car. Like I said, this standard is just defining the functionality. It's not an implementation by itself. In the second case of a library that can be used for message-based communication is the Corba library. Corba is a library that is designed for object-oriented programming. When you use object-oriented programming in a distributed environment, it does frequently happen that you would like to use a client-server type approach, which means you have a client, which is one computer, and a separate computer, which is indicated as a server. And then you might want to execute a certain service there on the client. For this, you call a certain method. The method is not implemented on that client itself, but the method is replaced by a so-called stub. The stub is used to transfer the parameters over some network to the server. The server is then unpacking the parameters there from the message, is performing the service, and is then returning the corresponding result back to the client. The problem with this design is that initially it was not conceived for use in a real-time environment, so therefore the access times for this approach are completely unpredictable because nobody has really thought about the required access times there. So therefore it became necessary to design a variant of CORBA that takes these real-time requirements into account. This variant is called real-time CORBA. Real-time CORBA is providing end-to-end timing predictability in a fixed priority system. So that means that you now have guarantees for the timing behavior for this communication between client and server. Also, with this design of real-time CORBA, we are respecting thread priorities between client and server for resolving resource contention. That means if on the client side we would like to access the same resource with different priorities, we assume that the same priorities also exist over here at the server side, so that we don't have a completely different behavior with respect to access to shared resources. Towards this end, the real-time CORBA system is also assumed to provide thread priority management, so we can increase and decrease the different priorities. And we also take care of priority inheritance. That means we address the problems resulting from priority inversion. Real-time CORBA is required to actually provide priority inheritance. Also, for real-time CORBA, we are required to have bounds on the latencies of operation invocations. So if we start a certain operation over here, we have a bound on the delay that can occur there. Also, in order to improve the real-time behavior, in order to reduce any delays, there is a pre-existing pool of threads, and whenever we would like to start a new thread, whenever we would like to create a new thread, we don't actually have to do this from scratch, but we can refer to threads that are existing there in the pool of pre-existing threads. So that was another method that we can use there in the case where we would like to use message passing. A third case actually that is using message passing is a method that is many times mentioned if you talk to people who are working on distributed systems. It is MPI, where MPI stands for Message Passing Interface. So like the name suggests, we do have a case of message passing. The MPI system or the MPI library is designed for high performance computing. So it's designed more for the environment that you see here on the right hand side. MPI is a very comprehensive, very popular library that is used by many researchers. If you talk, for example, to researchers in physics or in chemistry, you will in many cases find that they are using MPI on the mainframe computers on the data center on which they are working. MPI is available on a variety of platforms. It's not proprietary. It's not limited to a particular hardware platform. But it is mostly designed for homogeneous multiprocessing. That means we're assuming that the different processes that we have there in a network are all of the same type, so that we don't have to care about the different variants of the code to be executed. Now, more recently, that means after these data centers have become available, multiple processors became available in embedded systems as well. We do have these multi-processor systems on a chip, these so-called MPSOCs. And when they became available as a hardware technology, it became necessary to also have some means of programming them. And of course, people looked around and looked at high-performance computing and got the idea, well, okay, there is something that I could possibly use, and they tried to apply this MPI library also to MPSOX. However, the situation is somewhat different in that on MPSOX it takes about the same amount to communicate a certain block than it would take to copy that block into memory. That situation is completely different there in these data centers. In data centers, copying a block into local memory is a lot faster than communicating the same block into a different processor. So therefore, there was this issue when MPI was first used for MPSOX, the issue that the situation that we find for MPSOX is not well reflected in the design of the MPI library. To provide you with an example on how MPI calls could look like, I have included two such calls on the corresponding slides. This is the first slide. This slide contains a call to a MPI send primitive. There you see that as parameters we have the address of a buffer containing the message to be communicated. We are counting the number of items that we would like to communicate, and then we have a type identifier. We assume that all the elements in this block are of the same type. And then we have an identifier that identifies the process to which we would like to communicate this information. And we have a tag parameter. The tag parameter can be used to sort incoming messages. And finally, there is a parameter that refers to the set of processes to which the process that we are indicating here in this parameter actually belongs. We have several sets of processes, and these destination IDs need to be unique only within a particular set of processes. Finally, we have the function result, which indicates whether or not the call was successful. In contrast, we can also have a so-called non-blocking call, which means that the calling program can continue its execution even though the communication might not be really completed. So in this case, we have a call to a different function there in the MPI library. In this case, we have an additional I there, MPI iSend for immediate send. In this case, we have all the parameters like in the case before, and one additional parameter. This is a return parameter called request. The return parameter request allows us to check whether or not this communication actually has finished, and in this way we can wait in the calling program until the communication has actually finished. Now, with respect to MPI, we can see that the computation partitioning is explicit because we as programmers have to indicate how we would like to partition the computation. Also, as you have seen from the calls to the library, we have to explicitly describe the communication, and we have to explicitly describe the data distribution. Only some things are implicit in this approach. Synchronization is applied by communication. The expression of parallelism is also implied, and the way in which the communication is actually implemented is also implied. This means that most of the things are explicit. We as programmers have a hard time to actually program a parallel system in such a way, and therefore it has also been said that MPI is a kind of assembly language for parallel programming, because we as programmers have to do so much. We have to really care about so many things, and we would like not to care about so many different things. Also, when we are writing a program for parallel processing with MPI, we typically have a rough number of processes in mind, and if we have a drastic change of the number of processes, then we might have to rewrite our application. So we might have to indicate for additional for loops that these should also be executed in parallel. We might have to indicate that certain additional sections have to be executed in parallel if we are increasing the number of processes significantly. Now, unfortunately, MPI also has been designed for a non-real-time environment. So again, we have the problem if we look at this library from the point of view of somebody working in the real-time domain. We come to the conclusion that there are serious deficiencies there. We have no guaranteed timing behavior. So therefore, there has been the proposal to also design a variant of MPI that cares about the real-time requirements, and such a variant was proposed, for example, in 2001. MPI, the real-time variant of MPI, however, in contrast to OpenMP, does not cover such issues as thread creation and termination. And the idea is that MPI, the real-time variant of MPI, sits somewhere between the standard MPI and the operating system, so that if somebody wants to use a service for which timing is extremely important, could possibly refer to the corresponding service there of that layer explicitly. Okay, we can continue to discuss the different libraries that are available for communication in a distributed system. And in particular, if we look at message passing based communication. One library that can be used in that context is extending the plug-and-play concept that you might know from your computer. You might know that your computer typically provides this so-called plug-and-play concept, which means that if you add one additional piece of hardware, the computer is assumed to automatically detect how to actually install that piece of hardware into its local environment. The universal plug-and-play environment is the attempt to extend this into a full network. That means if you have a network of systems and if you add one component there, then you would also like to use this plug-and-play concept. And that means, for example, assume that at home or in your office you have somehow a network that has been designed by somebody, and in this network you might have a TV, you might have a hard disk recorder, you might have a home theater system, and you might have a printer, and you might want to add some additional piece of hardware there. Then according to this universal plug-and-play concept, this installation of this additional piece of hardware should be more or less automatic. So as an example, universal plug-and-play should discover printers, should discover storage space, and possibly also control switches in homes and offices. The UPnP concept is designed to exchange data. The idea was that it should not be possible to automatically transfer code or to call code. You can only exchange data, so in this way it's a little safer than an approach where we could also exchange code, because I think you could easily imagine that some problem that, for example, exists in the software of a printer could then spread to the other system components there in the system, which of course you would like to avoid. There is an agreement on data formats and protocols, and there are classes of predefined devices such as printers and media services, media service, and information is available from a website. If you would like to have more functionality there, you have to use a different library. One library is called the Devices Profile for Web Services. It's more general than UPnP in that you can also have code executed with DPWS. That's the abbreviation for Device Profile for Web Services. We are able to use messages across a whole network, and we are able to communicate events between the different partners there in the network. In such a DPWS system, we have services for the discovery of devices. So, for example, if you bring in a new smartphone into a certain environment, DPWS will be available to detect that new smartphone. Also, according to the standard, it's feasible to exchange metadata, so you might have metadata that describes the different devices in this network, and such data can also be exchanged. And then this facility also includes the publish subscribe mechanism, which means that some mobile phone that would, for example, like to subscribe to certain messages can announce that it would like to actually get copies of those messages, and then this mobile phone would get copies of certain types of messages. The overall protocol is lightweight because it has been designed to work even with small devices, and the idea is that these devices can also be used for automation. So if you think, for example, of a factory where you bring in new devices, the idea would be that in such an environment the new device can subscribe to certain messages and get, for example, copies of certain sensor values. It might be necessary to provide even more functionality, and even more functionality is available with JAXSTAR. JAXSTAR is a network communication protocol that is designed for peer-to-peer protocol implementations. That means you have a set of devices, all of which are considered to be peers. The communication there is based on a data format that is based on the XML standard. JAXSTAR can be implemented in many different modern computer languages, and the interesting feature of JAXSTAR is that it creates a virtual overlay. If you have a standard IP-based network, you do have the problem that you have some local IP addresses in such a network, and if you bring in new devices, you have the problem that these new devices possibly cannot listen to exactly the same subnet that you have already in, let's say, a local factory. With this virtual overlay network, you can make sure that you have an additional mechanism for describing the communication between the involved devices, even though the standard IP numbers might belong to different subnets. And this even works in case of firewalls and network address translation tables. So this was all I wanted to tell you about the communication libraries. Next, I do have 2 brief slides on databases, and I will briefly talk about databases. I guess you know that the key goal of databases is to store and to retrieve persistent information. Databases provide a so-called transaction mechanism, which means that we have sequences of read and write operations. For databases, it's very essential that changes are not final until they are committed. And for databases, we would typically request the so-called 4 ACID properties, where the 4 letters stand for the 4 properties that we request. The first is the property that these transactions are atomic. That means if we look at the state of our database, we will always see either a completed transaction or no effect of the transaction whatsoever. Second requested property is that the set of values that we are retrieving there from the database must be possible in the world which is modeled, so we shouldn't see anything that cannot happen in the real world. We also require these changes not to be visible, to be performed in isolation. That means we should never see some intermediate states of these transactions. And finally, of course, we require that these transactions are final, they are durable, because we would like the result of these transactions to stay there in the database. Now, these are general properties that are appropriate for data centers. However, again, we have a situation where something works reasonably well as long as we don't look at real-time systems. However, if we do have some real-time requirements, then we see that the approach that is usually taken for databases may get you into problems. Because for transactions, it can happen that they are aborted a number of times before they are finally committed, which means that the time that it takes to finally complete one transaction is rather unpredictable and therefore not very useful. Therefore, the whole concept is not very useful for real-time systems. Also, many databases are implemented using hard disk. And there we have the problem that we have with hard disk in general for real-time systems. We don't know how long it takes in general until the heads have moved to the right position, and therefore the access times are rather difficult to predict. We might try to find possible ways out of that problem. The one possible solution to the second problem is to use main memory databases. In embedded systems, frequently databases are rather small, so therefore it's possibly feasible to use a main memory database here. And with respect to this first problem over here, we might drop some of these ACID requirements, because otherwise it will be very difficult to implement these operations in real time. So this leads me to the summary of the first section of the presentation today. I talked about communication middleware. I mentioned pthreads and OpenMP. We looked at mechanisms for message passing based communication as well. There I looked at OSEC.com, I looked at Corba, MPI, JAXSTAR, and DPWS. And very briefly, I mentioned that we do have problems with databases in a real-time environment, because it is in general very difficult to provide timing guarantees here. So this concludes the first section of the lecture. Any questions?